Okay, so I am going to lead you through a description of your homework number 2. This is something we've done as a lab in the past, but this time I'm going to do it as a homework. I've changed some of the numbers, so this is different than what the previous assignment was like in past years, so please do this work on your own. Well, do this as new work, so don't go looking for a previous solution. There's some description here, but essentially what we're doing is based on the idea that carbon capture and storage is a mitigation method for climate change. So basically, to capture CO2 from a combustion source or to pull it out of the air directly and then inject it in the ground, which takes it out of the atmosphere, is a way for us to mitigate the impact of fossil fuel combustion on our atmosphere and thus to mitigate the effects of climate change. So you've talked about in your first lab and in lecture, we've also talked about carbon dioxide, big picture things, how much is emitted. We focused on China, Europe, and the United States. Now we're going to get local and say, okay, well, what if we really had to get down and do this for real? What will we do? Well, we would go to a power plant. And so if you look at this diagram here, this is the Fayette County power plant. If you drive from Austin to Houston on Highway 71, you'll see it on the north side of the road. And this is an approximately 1.6 gigawatt power plant. And what we're going to do is we're going to capture the CO2 from that power plant and inject it in the ground. And this exercise is to go through that process. And so here are some quantities. Conversion factor for pounds to kilograms, you should already know that. Definition of a ton, so everything talking ton here is going to be metric ton. 2 kilograms of CO2 per kilogram coal burned. That's a familiar number, hopefully, to you. And then we're going to assume that the coal is 10,000 BTU per pound coal. And so I ask you to do some calculations here to look at the joules per kilogram. And also I ask you to do, this is a straightforward meters cubed to foot cubed translation. But then let me just bounce through the questions here and try and give you some guidance to make the homework go a little bit more smoothly. So like I said, this is a 1.6 gigawatt or 1600 megawatt power plant. And I ask you to figure out how many BTUs does a power plant generate per year, given that power rating. How much coal would you have to burn in order to generate that amount of power? And how many tons of CO2, those are metric tons, that would generate. Okay. Now, the thing that's a little bit different, which we haven't talked about in class that much, and this is why I wanted to give you some guidance, is we need to do some geologic analysis to figure out where we're going to put this and how much room there is for us to put this in the subsurface. And so we're going to target a formation that's close to the Fayette County Power Project, and it's the Eocene-Wilcox Formation, which is a oil and gas formation actually in some places in Texas and the Gulf Coast. And the Wilcox Formation is a fluvial deltaic deposit. So basically means it's a river and delta deposit. So here's a diagram showing a river delta system. You can see depending on where you are in the system, you have more coarse grain or more sandy units versus more fine grain or more muddy units. We talked about net pay in class. Net pay is basically, I talked about it as the amount of a formation that contains oil and gas that we can produce. In this particular case, we're going to look for net pay as defined by permeability, which is a petrophysical property. And if the formation has high enough permeability, then it's a target to inject into, and we'll call that net pay. And so, like I said, to define net pay, we're going to use a permeability cutoff, but also people sometimes use porosity cutoffs. In order to do that, we need a log. So here's some log data. So looking at our log data, if I zoom out, you should be able to see the entire log. Okay, so if you look at this, we've got a log running from about a little bit shallower than 7,000 feet down to about 7,150 feet. And if I zoom back in here, I can show you that there's multiple tracks to this log. So there's 1, 2, 3, 4 tracks. The first track is a gamma ray track. We're learning about that in class right now. You can see it going back and forth, and we use a gamma ray to determine lithology. Then there's a permeability track, which is not a logging tool. It's actually taking samples from core that's recovered from the subsurface and taking a plug from that core every foot and making measurements. So we have permeability measurements on this scale and porosity measurements on this scale. And if I zoom in a little bit further, oops, that's as far as I can zoom in. Okay, well, I'm not going to zoom in any further then. Well, if you look at this scale, then you can see, let me just annotate this a little bit. Oops. Pull it back. Oh, here we go. Okay, so we zoom back in. Sorry. These are all pictures and they move if I don't choose them appropriately. So, okay, so, oh, I see. So here's a permeability scale, and you can see at 0.01 to 100 millidarcies, and it's a log scale, so this is 0.1, 1, 10, put the decimal points there, and so every bar is a factor of 10. So like I said, from 0.01 millidarcies to 100 millidarcies. And let me clear up my mess that I just made there so you can see it again. Okay, so that's the scale in permeability. Because it's a log scale, it's a really big difference from one side of the log to the other. Okay, then we have the porosity scale, and the porosity scale is actually reversed. So permeability is increasing from left to right, porosity is increasing from right to left. Here's 0, and it goes over to 0.18 or 18%. Okay, and so this is a linear scale, and it's divided into 1, 2, 3, 4, 5, 6 different divisions, and so that means 3% porosity or 0.03 porosity for every division. Okay, so erase that. The last track is depositional facies. So this is a geologic interpretation. Okay, and so you can see they've got the way these stratigraphic columns work is the thinner the column, basically we measure from here, the thinner the column, the finer the grain, the fatter the column, and this is measured from that bar. Thin column, fine grain, fat column, coarse grain. And so this is shalier, this is sandier. And you can see this is shallow water, low energy, shelf-based swamp. This is high energy, also shallow water, turns out, channel mouth bar. And so if we go back here, channel mouth bar is this guy right there. Bay swamp, well, the bay would be out here in the deep water, a swamp would be over here, but both of them are low energy, which would be fine grain. Okay? And so that's the geologic interpretation of where the sediment is being deposited. And you can see as we go through time, so if this is a geologic record, the top is younger, the bottom is older, so we're going in, whoops, what did I do? This is younger, that's older. Okay, As we go deeper in the column, we're going to older time. And so this channel mouth bar was deposited at some particular time. At later time, it got covered up by low energy deposits. So it's often better, actually, typically better to talk about time coming from older to younger. So let's start from the bottom up. So let's just say here we have, we start from this time right here. So we have pro-delta or shelf, that's considered deep water. Okay. So we start in deep water, and you can see it's fairly fine grained, and then as we go through time, you can see the grain is getting coarser. We go to delta front and to channel mouth bar. So we're going from basically going through a shallowing upward sequence. Let me write that down. Shallowing upward sequence. And so you can see where that fits here is we've got these, let me use a different color. Got these these muds out here in deep water. Okay. And so we've got, oh, this is deep, this is shallow, and this is mud, this is sand. And so at a particular time, we're out here depositing fine grained deposits. And then as this system progrades out, it basically fills in. I can try and make this a three-dimensional drawing. So it fills in, the shallow water, high energy stuff fills in over the top of the fine mud clay. So if we go from deeper to shallower, we'll go from fine grain to coarse grain. Hopefully that makes sense for you. And so if we look over here, we're sitting at a particular place on the surface of the earth. We're sitting there in deep water getting mud deposit, and then the delta is prograding out towards us and eventually covers us up in the mud, and we get sandier and sandier and sandier until we get to the channel mouth bar, which is our highest energy environment. Okay? And you can see there's basically two of these sequences. If I draw this, let's draw this in green. So there's a shallowing upward sequence there and a shallowing upward sequence there, and then we've got some other stuff going on in between. But essentially through time we're going through progradation of sediment out into the basin, fills up, and then the sea level rises for some reason, then we prograde out again. And so we're repeating these sequences, which is something that we study in a field called sequence stratigraphy, which if you take an advanced geology class, you'll learn more about that. Okay, so now I've got all this mess here. Actually, is there some way for me to... Maybe not. Oh, here we go. No. Let me clean this up a little bit, and let's talk about it some more. Okay. So that's the geologic interpretation. Now let's look at these engineering or petrophysical properties. Oh, hello, what's that? Okay. Look at these petrophysical properties, and I'll go back to the red pen. Okay. And so now we've got, here's an example of choosing net pay. And so what we want to do is pick everything above 0.1 millidarcies, and I do an example from 7,000 to 7,060 feet. And so what we're going to do, and let's see here. Can I use a ruler? I think I can use a ruler on here. Okay, so I'm going to draw a line which is at our permeability cutoff. And so our permeability cutoff is going to be 0.1 millidarcies. And if I can blow, well, yeah, I can just blow that up. We're doing this example which runs from 7,000 down to 7,060 feet. And permeability of 0.1 millidarcies. So I'll get that about right here. Okay. So everything to the right is net pay. Everything to the left is not. And so it looks like I'm somewhere around, let me use my ruler here again. That's the top of my net pay. And it looks like I covered it up, but there's a data point right here. So that's the bottom of my net pay for this section. And everything else, this comes close, but it doesn't quite get there. So everything else is not net pay. So I've got that interval, which is approximately 20 feet, and it's in the channel mouth bar, which is not surprising that that would be net pay. So now what you're going to have to do to get the complete, and that's what I've got written down here is 20 feet, so I got the right answer, supposedly. But what you're going to have to do is do this for the entire sequence all the way down to here, okay? And so you can just extend this net pay cutoff line and figure out where we have permeabilities that are above the net pay, or above the permeability cutoff. And you can see there's a lack of data from core plugs right there, but you can see it's the same depositional facies. So I'll let you decide what you think the permeability is in that section. So the purpose here then is to determine the net pay. So what is the net pay thickness in feet? And then you're going to go to the next page, and it's going to ask you, whoops, I don't know why it does that. Next page is going to ask you, if you go through your net pay, what's the average porosity? And so here we have, I'll use a different color here. Here's my net pay zone. This is the porosity data. And so what I'm going to do is just draw a line that runs that's about the average, okay? And then you want to read up on this scale what that value of porosity is. And you'll do similarly down here, okay? And all the way down from 7,000 feet to 7,150 feet. How much of that gross thickness is net pay? Okay, and so here I'm getting into the next page. So it says, what are the depositional facies of net pay versus non-pay? So you can take a look at that from the log data. It's going to ask you about the gamma ray response in the pay, which means net pay, and the non-pay sections. And where it talks more about that in class, and then it asks for your average porosity, like I said. Okay, now we're going to talk about the CO2 properties. And in your handout, this actually won't say 25 degrees C per kilometer, but let's say 20 degrees C per kilometer for the temperature gradient and surface temperature of 15 degrees C. And then we have a pressure gradient. So in order to figure out the chemical properties of a gas, you need to know the pressure and temperature conditions. And so you've got a depth in feet. Notice these are metric units for the gradients. So you're going to have to convert feet into kilometers in order to do this calculation. But let's just say that our depth was equal to 1 kilometer to make this an easy calculation. So then the pressure at 1 kilometer is equal to the depth times the gradient. Gradient is 10 megapascals per kilometer, so that's MPa. And so that gives me 10 MPa for my pressure, okay? The temperature at 1 kilometer is equal to the surface temperature, which is 15 degrees C, which I've assumed up here, plus the depth times the gradient, and the gradient is 20 degrees C per kilometer. So that gives me 20 plus 15 is 25 degrees C, okay? This is not your problem, this is just an example problem. You're at a different depth, you're at 7,000 feet, okay? But that's a way that you can calculate the temperature and pressure conditions, and then we can find out the properties of the CO2. Okay, so once you get those numbers for your particular case, then we can come over here and let's change to red. So we'll figure out the density of CO2 in kilograms per cubic meter. So each one of these lines here is a line of the material property of the CO2, 800 kilograms per cubic meter, 700 kilograms per cubic meter. There's a line on here, this black line is for 25 degrees C and 10 MPa per kilometer gradients per kilometer. We're not using 25, you're using 20, so that line is not your data line. So what you're going to do, so if we were to look at, well, you'll figure out some temperature and pressure, and then you come to this chart and figure out the density. So if we take the data that I had from before at 1 kilometer, shoot, okay, take the data we had from 1 kilometer as 10 MPa and 25 degrees C. That gives me 25 degrees C is right here. 10 MPa is right there, so that would put me right there. And that's a temperature and pressure gives me about 700 and I would say 30 kilograms per cubic meter. Okay, so that's the density. So that's how I'd figure out density. Okay, but again, this is not your example. This is an example I've just made up at 1 kilometer depth. You're going to be deeper than that, and different temperature and pressure. The other CO2 property we need is viscosity. Okay, so this is a viscosity chart, and again, you're given this gradient line, and so here this is temperature and pressure, and let's just say we drop, let's say our point was right there, then we're at 0.04 centipoise. Okay, let me erase that. So right, if we came in right there, we're at 0.04. Okay, so you'll pick some number which is going to be over in this area somewhere and figure out what the viscosity is in centipoise. Okay, so the other thing I didn't say is we're actually looking for supercritical CO2. So supercritical CO2 can be understood if we look at a PT diagram. And so, whoops, if I draw my very fat curves there, sorry. This is pressure, this is temperature. And so if we go over here at low temperature, high pressure, we've got a solid. We go to high temperature, low pressure, we have a vapor. Okay, and there's a boundary at low temperature and pressure between those two phases. and that's called the sublimation line. That means we go directly from a solid to a vapor. And then we typically have a melting curve and I'm going to run out of space here. Where'd my mouse go? Oh, there we go. Vaporization curve, or a boiling line, right? So we have liquid in the middle here, okay? This point is called the triple point, which is where solid, liquid, and vapor all meet. This point right here is called the critical point. And if we're beyond the critical point out in here, then we have what's called our supercritical fluid. And so what we're shooting for is the most dense phase of CO2 that we can get is when it's supercritical. And so that's what we're shooting for, supercritical CO2 when we're injecting, because then the more dense it is, the less space it takes up. Okay, so hopefully this is helpful for you to go through this. I know I'm taking a fair amount of time, but I think this will help you get through. Okay, so then we're basically figuring all this stuff out. Ultimately, then you're going to figure out the volume of CO2 you need to inject. Okay, and okay, the volume of CO2 you need to inject, actually, sorry. So that's what you're figuring up here, volume of CO2 to inject. You calculate that, and that's for a year's worth of Fayette County power project operation. And then you take that volume, you stick it in here, and you solve for the bulk volume of rock you need in order to store that volume. And that'll depend on how much pore space you have. And the pore space would be the bulk volume times the porosity. And then notice you need to know the saturation too, because how much of that pore volume is actually filled with the CO2. So if 100% of the pore volume's filled with the CO2, then you can inject as much CO2 as there is pore volume. But typically there's already water in there, and the water has to be displaced by the CO2, and it usually can't displace all of it. So we are going to assume that the saturation of the CO2 is going to be 50% or 0.5, okay? And so then you are then going to calculate what is this bulk rock volume you need in order to inject all this CO2. Okay, find my mouse again. And then here's a diagram that we just discussed in lecture. Given the net pay that you figured out from the log, or the strat column, what is the area you need in order to find that total bulk rock volume, okay? And here's a conversion for acres to feet. So how many acres are you going to need to lease, essentially, in order to inject your CO2? And the other thing, remember, if you read this little paragraph here, remember you have to pay to lease. So in Haynesville, people paid money to lease land in order to drill wells to produce gas and make money. Here, you're injecting CO2, which is a cost, but you're still going to have to pay the mineral rights owner, the subsurface owners, in order to drill wells and inject. So the last part of this is to take your volume of CO2 and convert it into barrels, and then knowing that that's barrels per year, and then convert that into barrels per day. And a typical injection well, or I guess a high rate injection well for water disposal might be something on the order of 10,000 barrels per day. Okay. And we're going to ignore this stuff. I'll write something different in the homework, but 10,000 barrels a day. So how many wells would it take to inject the fluid from this one power plant, this Fayette County power plant? Okay. So that's the next question. And the last question, and the point of this question is just kind of look at what scale of operation or business are we talking about? This Fayette County power plant is a typical coal-fired power plant. There's something on the order of 1,000 of these in the United States, and there's probably another 1,000 natural gas, but we're just going to look at the coal. So if you have 1,000 of these power plants, then how many wells, if you can reach my chicken scratch, for all the country? Okay. And the reason to ask that question is, like I said, to determine how big of an operation, how big of a business would this be. Partly because it would tell you how much it's going to cost, partly it's because it tells you how much of a job opportunity it is for petroleum engineers. Okay, so that finishes it up. I think I'll stop there. Good luck on completing the homework.